we can get started. So good morning to everybody, and thanks to Sunil and Mukul for this invitation to come here. But and I'm supposed to give 3 lectures, right, which I guess is slightly too much, not only for me, also for the people who are going to listen to this set of talks. Well, I am from this institute called Indian Association for the Cultivation of Sciences, and I happen to be a theorist. So the title of talks which was put up there will slightly get changed, because I'll tell you how to model so-called quantum materials. So the prospects and challenges in modeling quantum materials. So this will be the broad title of the talk, and it will be divided into 2 parts, part A and part B, and I think part B is scheduled today afternoon. Well, so the work, of course, received generous funding from SERB, and we also have a technical research center in our institute which aspires to do translational research. I should also acknowledge funding from DST. Well, so Mukul told me that kindly explain people what a quantum material is. To be honest, I mean, I also never had a very clear vision what a quantum material is. But what I knew is that all material requires quantum mechanics for their property. If you take a simple metal, right, to understand its metallic property, you need quantum mechanics. But is a normal metal like a copper or an aluminum, is it a quantum material? That's where the big question is. The answer is no. So all materials require quantum mechanics, but not all materials are quantum materials. So this is an important thing. So what are quantum materials, quote unquote, and which is of course one of the thrust areas of the research all over the world. So quantum materials are described by real quantum effects, right? So this is an important thing. And what are the real quantum effects? Topology of quantum wave functions, right? So this is one of the important things. And this topology of quantum wave functions is the essence of topological insulators, where the bulk state is insulating, but you have non-dissipating conducting surface states, and this is because of the topology of the quantum wave functions, right? So which gives this property. Second thing is quantum coherence, and quantum coherence is at the heart of the superconducting property, right? When superconductor forms, the BCS wave function, right, is described by this quantum coherence. And of course, the third thing is quantum fluctuations and quantum entanglement, and that appears in a spin liquid, and I'll tell you what a spin liquid is in more details as we move along. So spin liquids are materials where you have local moments, and the local moments, because of quantum mechanics, starts fluctuating, and this system is never ordered down to the lowest temperature you can think of. And why people are interested? Because these guys have interesting excitons, and which could be crucial for designing a quantum computer. Well, so these are of course hopes. So this is typically what I would like to mention about a quantum material, right? So these are the properties. If a material satisfies this property, then quote unquote, they are quantum materials. So let me briefly tell what I've been telling. So topological properties in quantum matter. Topology of wave function leads to dissipationless metallic states in band insulators. You can also have magnetic defects create topologically protected vortices. These are skyrmions, and they are believed to be important for the development of low power diseases. Magnetism, you can use classical ideas to explain magnetism, which is described in the first course in our solid state physics books. For example, ferromagnetics, most of ferromagnetism can be described by classical mechanics, right? But of course, a complete understanding requires quantum mechanics. And the most important thing, a low-like electron excitations in solid give rise to magnetic properties, and for which you need spin Hamiltonians describing spin interactions, and the spin Hamiltonians definitely need input from quantum mechanics. If you want to construct a spin Hamiltonian, and then from the nature of the spin Hamiltonian, you can talk about its excitations, and that definitely needs quantum mechanics. Frustration and spin liquid phases. This can arise from spin orbit coupling or lattice geometries, and this is something which I am going to describe in some details in this talk. And as I was trying to tell, spin liquids lack magnetic order, even to the lowest temperature that you can think of, right? And what they give you highly entangled states between spins, and that distinguishes them from paramagnets or even spin glasses, right? So this is an important thing. And superconductivity is of course what I told you, that this BCS wave function, right, is a very special wave function which essentially describes this quantum coherence. Right. So to summarize, quantum materials, entanglement beyond Fermi statistics. Right. So for example, electrons are anyway entangled, right? An electron can repel each other by Coulomb repulsion. This is one thing. But electron also repel each other because of Pauli's exclusion principle, right? So Pauli's exclusion principle brings in an entanglement because this guy will not allow a up spin to come near it, but it will allow a down spin to come near it. So this is the kind of an entanglement. So quantum material has to go beyond this Fermi statistics. So necessarily beyond independent particle picture. So what you see, the manifestation of quantum effect is a collective behavior of the electrons in a solid, right? So this is what a quantum effect means, right? And of course, topological properties of the wave function plays a very important role. So I guess in these two slides, I could give you an overview what quantum materials are, right? And what kind of things we would be interested in. So history of the research on quantum materials, and this I have taken from this nice review article by Tokura which appeared in Nature Physics in 2017. So from where this research got started, at the heart of it was basically two great ideas, and both of them attracted Nobel Prize. One was quantum Hall physics, another one was high temperature superconductivity, right? And this quantum Hall physics, I think yesterday you heard a talk on topological insulators and two talks on topological insulators, and where this must have been discussed in great length. So which brought in this concept of topology, topological current, Berry phase, anomalous Hall effect, spin Hall effect, even multiferroics, and topological insulator spintronics, and which will emerge into topological electronics and quantum computation. High temperature superconductivities brought strong correlation at the forefront, right? And high temperature superconductivity told us that you have to go beyond independent electron approximation to understand materials, right? Which was quite well done, right? And that brought in new particle fractionalization. By nanophysics, I think we mean here physics at reduced dimensions, in 2 dimensions or even in linear chains and so on, right? So this is what it brought in. And of course, this gave rise to this birth of this advanced spectroscopy. I would guess particularly photoemission spectroscopy went to its height after the discovery of high temperature superconductivity or angle resolved photoemission spectroscopy, right? And of course, these days people talk about terahertz spectroscopy to see low-lying excitations. So you can see this as gift. And that left to, of course, the desire would be to have above room temperature superconductivity and motronics, right? So this is what the future is. So what I would like to say, that essentially there are two concepts, namely quantum Hall physics and high temperature superconductivity, right, which was discovered maybe 35, 40 years ago, right, which has essentially delved into or bifurcated into a new realm of physics, right, and that's what we all are working or aspiring to work, right. So, and that's the reason you can see these are the ideas, right, which eventually attract Nobel Prize. Well, so we would all be interested in emergent phases and emergent functions of quantum matter and what brings about that, right? Because as I told you, the theme of my talk would be to model quantum materials, right? So, and I need to identify. So how this happens? This happens because of strong interplay of the spin, charge, orbital and lattice degrees of freedom, right? Spin of the electron, charge of the electron, orbital degrees of freedom if an electron has, and of course the lattice degrees of freedom. And on top of it, right, if you can add topology, right, here, then of course you go ahead and have emergent phases which and functions of these materials, right. So this is what, so this is something which has to come if you would like to make a reliable model for our quantum materials. Well, so as I said that this interplay of Coulomb repulsion, orbital bandwidth or orbital degrees of freedom, crystal field, elastic strain, right. So, and to describe you of course require a quantum description, and the starting point of the quantum description is of course the independent particle picture. You have an interacting electrons in a solid, and by some means you have to get rid of the interactions and try to come up with some rest electrons, right, which no longer interact with electron but move in an effective potential which mimics this thing. And this was done again very successfully by Walter Kohn, by what is known as density functional theory. So I'm not getting into density functional theory, but what I'll get into is this Hamiltonian. So if I want to understand the electronics properties of a solid, right? So this is a solid, these are the ions and these are the electrons and most of the valence electrons, right, which are moving around in a solid, and they of course interact with each other. The first term is the kinetic energy of these electrons. The second term is the confining potential, and what is this? Is the attractive potential between the electrons and the ions. As a consequence, the electron does not leave the solid, right? This ionic positive background gives you this. And then of course we have this celebrated electron interaction term. Up till this term, you can exactly solve the Schrodinger equation. There is no problem. But this term brings in all interesting features, and this is where is the bottleneck. So this term we'll call an non-interacting part of the Schrodinger equation, and this part we'll call an interacting part. And please keep this in mind, right? So because I'll be referring back and forth to this. So what density functional theory does? Density functional theory reduces this interacting problem to an affecting non-interacting system. So right, so you have this interacting system, and density functional theory provides you with a recipe so that the particles are no longer interacting with each other, and so they are non-interacting particle but moving in an effective potential. And what this Nobel Prize winning work does, it gives you a recipe how to construct this effective potential. And this theory of course has success, right? And this is, so let us first see what are the success of this theory. The first success of this theory is the predictions of so-called band structure or single particle theory. Of course, it can tell us in many cases which will be metals and which will be insulators. So for example, if you have even, so because each band can accommodate 2 electrons by Pauli's exclusion principle, as a consequence, if you have even number of electrons per unit cell, you can definitely have an insulator. Or in some cases, for example, in carbon or silicon, or in some cases, if the bands overlap with even number of electrons, you can even have a metal. But one of the important thing is that this theory tells us that if you have odd number of electrons per unit cell, the system will always be a metal, because a band can accommodate what? A band can accommodate 2 electrons. If you have 1 electron accommodating in a band, under no circumstances it can become an insulator. It always has to. So if you want to know when this independent particle picture breaks down, the thing is that you have an odd number of electrons, the system is an insulating, right? So then you know that this independent particle picture is no longer going to hold good. Well, this picture has success. For example, it can describe the electronic structure of graphene, many Dirac materials, topological insulators. And why this single particle wave function can describe topological insulators? Because the non-triviality essentially brought in by the spin orbit coupling, right? And that makes this trivial single particle wave functions non-trivial, and that gets reflected in a band inversion and eventual topological phases. But in today's talk, I'm not going to talk about this topological insulators, but because I guess it was covered in details yesterday. But I just thought that even a single particle picture, right, is successful in describing a class of quantum materials, right, where spin orbit coupling is important. So failure of band theory, right? This is what I was pointing out. For example, cobalt oxide, and total number of cobalt oxide is that you have 9 electrons for cobalt and 6 electrons from oxygen, and that is an odd number of 15 electrons. So band theory or electronic structure, normal single particle theory predict cobalt oxide to be a metal, while it is the toughest insulator that you can think of, right? So as you can see, another example, the celebrated example, of course, high TC cuprates like lanthanum cuprate, right? The parent compound copper is in D9 configuration, again odd number of electrons, right? But the system happens to be a insulator, but if you do a single particle theory, it will be predicted to be a metal, right? So this is what the failure of density functional theory or failure of single particle picture, and where we have to bring in this importance of interaction effects, right? So this is where the things are. Well, so again, I'll start with this non-interacting part of the Hamiltonian and the interacting part of the Hamiltonian. So for a correlated system, the situation is something like this. So for example, this is of course a street in Pune or Mumbai or in Kolkata, right? So now you can see, you can never map this problem to a problem that a car will move independent of the other cars, right? So you can see that I have to care about the cars in my neighborhood, right? And this is an aspect right, which has to be tweaked into my model, right. So this aspect which is brought about by electron-electron interaction has to be tweaked, and this is where the independent particle picture fails, right. So this is where the problem is. So what you can do, so this is your full Hamiltonian, you find some one particle basis, right, any basis that you like, and what often one does, one takes a tide binding basis which is single particle basis and tries to represent the Hamiltonian in that basis. If you do this, then this is a non-interacting part, it will have an on-site energy, it will have hopping, and this is typically a tide binding model that you learn in your first course in solid state physics, right. And then what you are having because of electron-electron interaction, you are going to have this interacting part, and this interacting part can be pretty long ranged, right, because this is what it is, although the bases are localized. So you can see this is a 4-center integral that you have to solve, and this can be pretty long range. Well, this model can be solved for small atoms and molecules using quantum chemical methods. Even we do that. We also try to solve such models by using a technique called exact diagonalization. But then we are restricted to a very small size of the cluster that we handle, which is essentially instead of taking an Avogadro's number of atoms or molecules, what we do, we only take few atoms in a site, and then we start working on that. So what we need to do, so this is of course a model in its full glory. We need to remove degrees of freedom. What do I mean by degrees of freedom? For example, if you are working with cobalt oxide, then there will be cobalt d orbitals, oxygen p orbitals, so on and so forth. So you cannot work with this entire basis, right. So what you have to do, you have to essentially look at which are the orbitals which are near close to the Fermi level, identify them, right, and that becomes the active orbitals in your basis, right. This is what you go ahead and do. And also what you have to do, you have to essentially trim the interaction terms, right. Instead of taking a long range interaction, you say in a solid there is a screening, and as a consequence of screening, right, the Coulomb interaction is short ranged. Only 2 electrons at a particular site will see each other. If the electrons are at a different site, they will not see each other, or they will not care about the Coulomb interaction between them. And this is what the idea of celebrated Hubbard model. Until date, we are not able to solve that simple model exactly, right. So this is where the problem lies, right. So what is one of the thing to be done? Model Hamiltonian with chemical realism. Please feel free to ask me questions at any point of time you wish, because I think, well, so key ingredients of quantum matter leading to emergent phases. So this is what I have taken an example, say for example lanthanum copper oxide. It's not quite a lanthanum copper, it's in fact a perovskite. Lanthanum is a body center tetragonal, but so we have a transition metal enclosed in an octahedral cage of the oxygen, and this is some other. So this is something like AbO3 kind of a compound, right. So SrVO3 kind of a compound, right. So this is my strontium, this is my vanadium, and this is my oxygen octahedra. So one of the key ingredients, of course, crystal field splitting, because the vanadium d orbitals, right, so they will no longer remain degenerate because of the influence of the crystal field. They will split into T2G, EG, and so on. So that this piece of information has to go into your model. Of course, electrons from one vanadium will hop to another vanadium or to oxygen and so forth. So you need kinetic hopping. You need on-site Coulomb interaction. As I told you, that will not take the long-range Coulomb interaction. We'll only say that if 2 electrons are found at a particular site like this, then only Coulomb repulsion acts. If the electrons are here, for example, then there is no Coulomb interaction between them. And this can only happen if the Coulomb interaction is massively screened, right? This is what one of the thing is. And on top of it, you also have to include spin orbit interaction. And so these are the basic interaction that has to come in. If you have multiband, then of course you have a Hund's exchange, because if you have 2 orbitals available per side, then 2 parallel spins will lower the energy in comparison to 1 parallel and 1 anti-parallel. So I'll get into that, right. And in addition, if your lattice is frustrated like triangular Kagome, or if you have a honeycomb lattice, that brings in exciting features. That's what we are going to tell. So as a consequence, my Hamiltonian is something like this. You have hopping plus on-site energy, this is these 2 terms. You have Coulomb repulsion, this is this term, and of course spin orbit interaction, this is this other term. And then what you do, you put it in such a lattice, and then if you are able to solve this model, then you start seeing all kinds of exciting properties. Right, people seeing the last row, is the slides visible to you? Yes, because I was sitting somewhere there yesterday and I could not see the slides, so I was just wondering that. Good, so this is what it is. So emergent phases, this will define our talk, what we are going to do. So this is my Hamiltonian, right, hopping Coulomb correlation and of course there is something which I have not talked about. This is disorder, right? So, and this is of course I have not talked about. I'm not going to talk about in this talk, but this is a very important component, right? Even a non-interacting system in the presence of disorder, the electronic states can become something different from block states. They can become Anderson localized. So disorder plays a very important role in condensed matter physics, and all samples, real experimental samples, continue to have disorder, right? And that's an important thing. So we should keep that in mind. Well, so if I consider this Hamiltonian, then I basically have two axes, u by the hopping and lambda by the hopping, right? These are the two axes, and these two axes can be divided into four quadrants. Is it okay? Right. So for example, if my u is small and lambda is small, so then it's my simple materials, and this is what you learned in your first course in condensed matter physics. Ashcroft-Marmin's book precisely describes that. So now what I can go ahead and do, I can basically, so this is what both of them are suppressed. So I can bring in one of the interaction. So I walk along this axis, and this will essentially give us this traditional Mott insulator. That means although you have odd number of electrons, but the system will become insulating, and that is what is known as Mott transition. And phenomenon associated with Mott transition, if you can tailor Mott transition, and that is what is known as Mottronics, right? So this is what I'm going to tell you. So 3D transition metal oxides are the ones which come into this picture. You can have multiferroics, low dimensional quantum spin systems, and so on. If time permits, I'll talk about multiferroics in this talk. So this axis is something that I'm going to talk in this part A of this talk. Okay. So now what I do, I suppress U and bring in. So, and of course, in some special case, right, when U is very, very greater than T, then you can map this itinerant model into a localized spin model, which is known as Heisenberg model, right? So that this is what the parent compound of high TC cuprate is. It can be described very well by a 2D antiferromagnet, right? So this is because U is very, very larger than T. Well, so now what I am doing, now I am suppressing U and bringing in lambda, right? And as a consequence of spin orbit coupling, you can have band inversion, and that is a key in deriving this topological insulator. As a consequence, a single particle theory with spin orbit coupling can describe topological phases or bring in non-trivial phases in topological, describe non-trivial phases in topological insulators. Well, so this is what it is, and I'll also show you one kind of spin orbit coupling comes from the radial electric field of the electron. But there can be sources of other fields in a solid, and that gives rise to phenomena like Rashpa effect and Dresselhaus effect. So as I move along, I will explain you what distinguishes a normal spin orbit coupling from a Rashpa or Dresselhaus spin orbit coupling, and that has an useful impact in quantum materials. Well, so now what is the next stage? The next stage is of course to bring everything, and this is something which will cover in the part B of our talk. This scenario I'll cover in the part B of the talk, right? And now if you again find U and lambda are comparable and very, very greater than T, which happens in iridates, right? So then what you are going to have, what is known as a Kitaev model, where exchange interactions are bond dependent, and this such kind of thing Kitaev is shown exactly, that leads to what is known as a Kitaev spin liquid. So you can see that if you can identify materials, because quantum technology is introduction to materials and devices, so you can look for these aspects in a material, then you can even predict which guys should be a Kitaev material or not, and I guess after the end of the talk possibly that aspect will be clear to you. So I guess I could tell you the part A of the talk is essentially the y-axis, part B of the talk is essentially the x-axis and the combination of y and x-axis, right? Well, so Sunil, can you tell me how I'm doing with time?
You have more than half an hour.
Okay, good. So this is my crystal field splitting, which I'm not getting into details. As I told you, that if I have a system like this, a vanadium atom in an octahedral or a transition atom in an octahedral, so the d orbital gets splits, and this is what is crystal field. Spin orbit coupling is something which I'll talk a little later, but spin orbit coupling again further splits this spin degenerate threefold T2G orbitals into a fourfold J3 and J and this is something which, but spin orbit further splits this T2G state. So this is something which should be kept in mind. Of course, and these parameters can be estimated from a DFT calculation. So as I told you that I've taken this example for strontium vanadium oxide, and if you simply take the non-interacting part of forget about the electron correlations, assume that and assume an independent particle picture and do a, so strontium vanadium oxide is an insulator. It has an odd number of electrons, a D1 system, it's an insulator, right? So it cannot be described by a band theory. So you would like to do something so that it could be described by a band theory, right? So this is what the idea is. Well, so if you do an electronic structure calculation of SrVO3, then you will find that all my so this is my Fermi level, all my oxygen 2p bands are occupied, right? At the Fermi level are the threefold degenerate. Of course, the degeneracy is only at the gamma point. It breaks as you go to the other point. These are my T2G orbitals, right? Which straddles the Fermi level. Above it are the EG orbitals, and then what you have strontium 4D and strontium 5s, right? So this is what you can see. And T2G orbitals in principle can take how many electrons? It can take 6 electrons. But here, since the number of electrons is much less than 6, so you can see this straddles off. As a consequence, it gives you a wrong description of the system. It becomes a metal, right? And now if you add Coulomb correlation to it, it will become an insulator, a Mott-Hubbard insulator. So as I told you that we have to integrate out orbital degrees of freedom, right? So that means if you want to model only these T2G orbitals which are at the Fermi level, these 3 orbitals which are at the Fermi level are important to model this system, right? You don't have to care about the oxygen P or the strontium or the vanadium EG orbitals. And this is something, so this is what should come in your model, and this is what we can extract by a method which we'll call a downfolding method, right? We can only extract these 3 orbitals, but when we extract these 3 orbitals, these are effective orbitals. So this is my vanadium XY orbital, and it, of course, these orbitals, of course, has the information of the oxygen with whom they hybridize, right? So this is what we go ahead and do. Well, so this is done. So the Hamilton is divided into an active and a passive states, and here active orbitals are vanadium T2G and passive are the rest. And then you can do this what is known as Lewdin partitioning, and then if you freeze this energy to a particular energy value, then you can essentially recover your active basis only. So this is a technical part, let's not get into it, but and this is what is known as NMT or downfolding method proposed by OK Anderson. Well, I'll just give one example what we do. So for example, if you would like to do this lanthanum cuprate, right, I'll not get into this slide in details. If you go to lanthanum cuprate, so you can see copper will be in D9 configuration. If copper is in D9 configuration, then only copper dx square minus y square orbital will be at the Fermi level, and as a consequence you can see only copper dx square minus y square is the Fermi level. You can copper dx square minus y square, and one can go ahead and extract. If you want to do a model for high TC, a single band Hubbard model, right, suffices, right? This is what, so this is what we showed long time back. So you can only extract the single band with these hoppings, right? And this also told us how you can distinguish lanthanum cuprate from the mercury cuprate, when mercury cuprate has a higher TC compared to the lanthanum cuprate, so on and so forth. But because of the paucity of time, I'll not get into this discussion. But I'll allure you. So what happens here, you just to tell you, because you can see that the hopping in the case of lanthanum cuprate are much weaker compared to thallium and the mercury cuprate. You just see the second nearest, so these are nearest neighbor hopping which are identical, but if you look at the second nearest neighbor hopping, you can see for the thallium and the mercury they are much higher, right? And third nearest neighbor hopping is also higher compared to lanthanum cuprate. This distinguishes lanthanum cuprate from the mercury and the thallium cuprate which has a higher TC. And this happens, so this hopping, right, happens because of an out of plane orbital which is called an axial orbital. Well, so this was the story of high TC, and this is the work which was done right to 20 years ago. But then this work became relevant when superconductivity was discovered in nickel analog of cuprates. Neodymium nickel oxide or lanthanum nickel oxide or praseodymium nickel oxide, they happen to be superconductors. So then we also looked at its electronic structure, and then we figured out, like copper dx square minus y square, you have a nickel x square minus y square band which straddles the Fermi surface, right? But in addition to that, this axial orbital which promoted hopping in the cuprate but was not at the Fermi surface, now comes at the Fermi surface, right? So this is what. So we proposed to understand neodymium nickel oxide, right, you need a 2 orbital model, because there are 2 orbitals, right, which comes to the Fermi surface, and this is happening because of the active role of the neodymium F and the praseodymium F. And you can say lanthanum nickel oxide is a much lower TC, and this brings in, and in fact we did a so-called mean field calculation, and we could predict things, and this 2-band superconductivity was eventually seen in an STM data. So this is a relatively new work. What I'm just trying to tell, even just deriving a simple tide binding model, right, for these materials, right, you can learn a lot, right. Once you have derived this non-interacting part of the model, then put an interaction, right, again based on your intuition, and then you can start working it out, and then you can see. But this understanding this chemical realism happens to be one of the important things. Well, so this is as far as the on-site and the hopping is concerned. So now let us go to strong correlation, right? What is strong correlation? So let us bring in 2 sites, right? A particular site can accommodate 2 electrons by Pauli's exclusion principle, but I am taking it only 2 sites just to understand, but your solid will have n, and n is equivalent to Avogadro's number. And this is what I will say on a half filled situation, right? Because now what you can have, so now let us consider our Hamiltonian, and the Hamiltonian has this non-interacting part, and non-interacting part will allow this hopping, so the electron merely hops here, and if the electron hops here, right, so then it lowers its energy in principle, right, because this T lowers its energy. It gives you a bandwidth, so electron can merely move around. So 1 electron per site, according to independent particle picture, it will be a metal. Right, so this is what you clearly see. If you go ahead and look at its DOS, right, so electrons can hop, so it's a metallic DOS, and this is what happens, right. But there are systems, as I told you, like high TC cuprates, they are half filled systems. Copper is in D9 configuration, which essentially implies there is only 1 electron in copper x square minus y square system. So this is just like this, but this guy happens to be an insulator, right. So for this you have to include this term U, right. If you include this term U, means if 2 electrons are sitting at the same site, they have to pay a price of this U. So this is not a favorable situation, right? This is not a favorable situation. So U means that if there is an U, the electron will not be happy there. So what it does, it essentially flips back and like to be localized there, right? So electron essentially loses its itinerant nature, right, and would like to be localized there. If the electron is localized there, which this implies what? It implies that you have to pay a price to hop, right. So as a consequence, you have a set of filled states separated from the empty states by a gap, and this gap, the strength of this gap will be equal to U. So this is precisely what happens, and this is what is a Mott insulator. This is what the physics of a Mott insulator, and this is what is your Hubbard model is, right. This is what the physics of a Mott insulator is. Right, so strongly correlated systems, this y-axis, I have 2 parameters, T and a U, right? And so this is what my Hubbard model is. Now, if your T is very, very greater than U, right, then of course you have a metal. So T is very, very greater than U means you have very broad bands. Broad bands mean the road is very broad, right? Even if you lot many cars, the cars can avoid each other and move freely, right? And this is where your independent particle picture holds and density functional theory works out fine, right? So this is where the story is. Well, but when U is very, very greater than T, then what happens? The road becomes, the bandwidth becomes narrow, because T describes the bandwidth. The band becomes very narrow. If the band becomes narrow, the electrons start seeing each other, just like the car. The cars will now start seeing each other, and have to bring in this physics of U, right? So narrow energy bands, tendency of localization, so the electrons start seeing each other. And if the electrons get localized, right, then you can essentially forget about their charge degrees of freedom, right, and you can essentially replace that the spins interacting with each other, and that brings in this concept of Heisenberg model and so on and so forth, right. So now you can see, if U is very, very greater than T, then you have an insulator. If U is less than T, then you have a metal, right. So but you can now go ahead and control this U and T, this ratio, by some means. You can apply pressure, external pressure, you can apply chemical pressure, right, and you can tune this metal insulator transition. And I only talked about a Mott Hubbard insulator. There are also other kind of insulators which are known as charge transfer insulator. Charge transfer insulator can be a positive charge transfer insulator, negative charge transfer insulator. If I start saying that, then I mean I possibly would be giving a course here, but it's not possible. So controlling U and T, leads to metal insular transition, and this is the essence of motronics, right? How do you do this? Well, so as I told you, this is an effective model. We wrote this Hubbard model, right? And this is this copper, right? You can see copper dx square minus y square has 1 electron per side. It can accommodate 2, but it has 1 electron per side, right? And if u is very, very greater than t, then what you do? You take u as a non-perturbative part and t as the perturbative part, and simply go ahead home and do a second order perturbation. And if you do a second order perturbation, then what you derive? You derive an Heisenberg model where j is equal to 4t square by u, and which is also known because the electron is not able to hop, right? So better it sits in an antiferromagnetic lattice, and this is essentially the physics of high Tc cuprates. So you can see one electron, if you have a situation where there is 1 electron per site, right, and u is very, very greater than t, then automatically Hubbard model reduces to an Heisenberg model. Now if you start doping it holes, then of course that itinerance has to come in, and that is the essence of a TJ model, right? So this is what Phil Anderson described a TJ model to describe the physics of high temperature cuprates. Well, so as I told you that Heisenberg model has a symmetric exchange interaction. If you switch on spin orbit coupling, then this exchange interaction becomes antisymmetric. So this is what is known as the Zalosensky-Moria constant, right? And that leads to canting of spins in the presence of spin orbit coupling. But you don't have to care about spin orbit coupling as far as this talk is concerned. So requirement for DM interaction or Zalosensky-Moria interaction is the presence of spin orbit coupling and lack of inversion symmetry. So if you have a canted spins, right, the canted spins, right, would essentially tell you that in the presence of, that there is a spin orbit coupling, or there is a local breakdown of inversion symmetry. Well, so good. So interactions in a multiband Hubbard model. So multiband Hubbard model brings in some more complications. If you have 2 orbitals per site, right, so then what? So for example, in copper oxide, you can see there are 9 electrons, right? 6 electrons are accommodated in the TQT states. You have a pair of EG states, which is 3z square and x square minus y square, which can accommodate, has to accommodate these 3 electrons, 6 plus 3, 9, but these guys can accommodate 4 electrons. So which one will take less number of electrons? So this is a kind of a problem which these guys face. So then there is a local distortion which is known as Jahn-Teller distortion, which lowers one of these orbitals, right? And this Jahn-Teller distortion lowers one of these orbitals means in the case of cuprates, it is a z square orbital which gets occupied, and the x square orbital is higher, right? So what I'm saying, in the case of cuprates, it's the z square orbital which is lower, and the x square minus y square orbital is which is higher, right? And as a consequence, if all the orbitals, right, have the same spin, right, then we say this is a ferro-orbital ordering, right? So this is what is known as the cooperative Jahn-Teller distortion, ferro-orbital ordering, and so on, right? And this, of course, brings in additional terms in my Hamiltonian, because 2 spins can be here. This is your Hubbard U. 1 spin can be here, another spin can be here. Then you lower your energy by virtue of this Hund's coupling. In such a situation, you don't lower the energy, you only have this U prime. U prime means the U between 2 orbitals, right? So this adds complication to the model from a single band if you want to go to a multiband. Right? So search for novel quantum materials, and I think Sunil should tell me how much time do I have?
About 20 minutes.
20 minutes, oh good. So then, I think you are sure, right, that 20 minutes, okay. No, it's okay because I find, good. So I would like to search for a quantum material, right? So, and I gave you some criteria to search for a quantum material. So what do I do? So let us be optimistic. Let us consider only copper D-based oxides. And what I know about copper D-based oxides, that these are 3D systems where Coulomb correlation is supposed to be large. Spin orbit coupling is relatively less. So I'm not talking spin orbit coupling in this system. And in addition to that, copper has transition metal oxides, right? Like copper oxides with small spin, right, like copper 2 plus D9, where, as I told, there is only 1 spin in the copper x square minus y square orbital, which means the value of the spin is s equal to half, right? So this is a low spin. If you have a low value of the spin, right, then there is quantum effects, right? And if you can make the dimension, 2-dimensional or even a 1-dimensional chain, Heisenberg chain, the quantum effects dominates, right? And as a consequence, things becomes. So, and if the important interactions are only in 1 and 2 dimension, exhibits variety of noble properties like spin gap states, spin charge separation, quantum criticality, and so on. So these guys, these cuprates also has orbital degrees of freedom. As I told you, that you have the freedom of filling up 4 electrons, but you have only 3 electrons at your disposal for a D9 system. As a consequence, these electrons don't know which orbitals to occupy, right? That there's this dichotomy which exists. Right? As a consequence, there is an orbital degrees of freedom, and that essentially promotes a cooperative distortion, which is known as a cooperative Jahn-Taylor distortion. And how the Jahn-Taylor distortion will happen, that depends on the physics at hand, depends on the structure at hand, right? So copper has this thing. So orbital degrees of freedom, strong correlation, right, which leads to structural distortion and magnetism. And this I'll show you is one of the key things for a multiferroic property. And also, if you have a non-centrosymmetric system, then there can be SOC, and SOC can give rise to this antiferromagnetic exchange, which are your DM exchange, right? So, and of course, the model for cuprates will always be an Heisenberg model, right? So the spin model for the cuprate should always be an Heisenberg model. So if I'm looking for a new material, copper-based oxides happens to be a very fertile ground, and that people have been working a lot, right? So what I'm going to talk about, I'm going to talk about this multiferroics, right? And what is multiferroics? So you all know about ferromagnetism, right? So ferromagnetism, magnetic moments align on the application of a magnetic field, right? You have a nice hysteresis curve M versus H. What is ferroelectricity? Ferroelectricity, electric dipole align on the application of an electric field. Again, polarization versus field, you have a nice hysteresis loop. And as I told you, that both of these guys can be described pretty well within the realm of classical mechanics, and both of these topics appear in your Ashcroft-Mermin's book, right? But what I would like to have, I'd like to have a system where you have both magnetism and ferroelectricity, and this is multiferroic. And this coupling between magnetism and ferroelectricity can only be brought about by quantum mechanical effects. Now no classical effect can work, right? These are the two different order parameters, and they would now like to couple with each other. So one of the things which would play an important role is the symmetry of the material, A. And once the symmetry is satisfied, then a quantum mechanical effect has to happen, so that is two order parameter. And if this happens, right, so then of course I'll have a next generation of electronic memory, and this is what is multiferroics is, and this is what is your quantum technology, right? This will bring in your quantum technology in the business, right? And what is ferroelectric? So you have a 4-state memory, because now you can tune electric polarization to the application of magnetic field, magnetization to the application of electric field, and of course your H versus M and E versus P remains, right? So you are going to have this magneto-electro-random access memory, which will have the best of two worlds, right? So this is something which is an important. Of course, this multiferroic material has to operate at room temperature, right? So this is where the challenge of the work is. So I told you that I can have a material. Well, so what I'm going to talk here, so let's not get into this detail, that I'm going to talk about magnetoelectric multiferroic, where magnetic field will try to control polarization, or an electric field may control magnetization. Right. So what are the symmetry requirements, right? If you have a magnet breaks time reversal symmetry, right? So this you can see, because if you have a current, it has a magnetic field. If you reverse the sense of the current, the direction of the magnetic field changes, which breaks the symmetry. So a magnet essentially breaks time reversal symmetry, and that's what you see. So if you have a magnet, or magnetism requires the breaking of time reversal symmetry. Well, ferroelectrics have to be an insulator, and they have to break an inversion symmetry. There has to be an off-centric of the dipoles, and that only will give you a finite dipole moment. Otherwise, dipole moments will cancel each other, right? That's what happens in a metal. The dipole moment gets screened out, right? You have to have an insulator and a non-centrosymmetric insulator. That means that has to break inversion symmetry, right? So now if you want to have a coexistence of both this order parameter, then the system should break both time reversal symmetry as well as inversion symmetry. And these are what are known as polar materials, right? So if linear magnetic-electric effect, where polarization is connected to magnetization and, a magnetic field, and magnetization is connected to electric field, right? So this is the susceptibility, right? And for a finite chi, both time reversal symmetry and inversion symmetry has to be broken, right? So this is a key thing which you require to realize both magnetism and ferroelectricity. Good. So ferromagnet, right? So ferromagnets usually have partially filled d shells. If you have a filled d shell, right, so then there is no scope of magnetism. So you have to partially fill d shells, then the spins doesn't get compensated, you have magnetism. On the contrary, for ferroelectric, you prefer to have an empty d shell, right? Because if you have an empty d shell, so for example, if this d shell is empty, then it feels an electrostatic repulsion or even an electrostatic attraction from the ligands, and that leads to off-centric, right? So you can see realization of what ferroelectricity and magnetism are counter intuitive, right? So is the coupling chemically forbidden? Well, so then came this two kind of multiferroic. Type 1 multiferroic, where magnetism and ferroelectricity have their independent existence. These guys have high critical temperature and weak coupling between the order parameters. And I'll talk about only this case, right? So for example, if you have bismuth iron oxide, bismuth has a lone pair, right? Bismuth 6s electrons have a lone pair. As a consequence, that leads to off-centric nature or breaks the inversion symmetry, and iron is of course magnetic. So you have this existence of two independent order parameter, namely off-centricity described by the bismuth and the magnetism described by the iron. So they are two different order parameters, but somehow they are coupled, and this coupling is weak. But that is not our requirement, right? Our requirement is that this coupling between these two order parameters should be strong. As a consequence, changing one, the other will have a larger response. So this is the case of improper ferroelectrics, where electronic, namely spin, charge, orbital order induces an electric polarized material that is otherwise structurally symmetric. So for example, what happens? So you have a centrosymmetric crystal structure below a certain temperature T, right? Now you lower the temperature, system becomes magnetic. If the system becomes magnetic, this magnetic system, right, modifies the lattice, right? It breaks the inversion symmetry, and as a consequence, ferroelectricity appears. That means the triggering factor of this is magnetism triggers ferroelectricity. So first magnetism followed by ferroelectricity, right? And this can happen by a variety of means, and one of these means is, for example, what is known as exchange friction. So this is this compound Ca3COMnO6, where your cobalt and manganese are along a linear chain in such a way cobalt and manganese spin in one, first two are up and the next two are down, right? So when the magnetic order sets in, right, so then the up spin, right, they tries to move away from each other, and up down spin tries to come closer to each other. As a consequence, the structure breaks inversion symmetry, and as a consequence, it becomes ferroelectric also, right? And this is what is known as exchange friction mechanism. I'll not get into it. So for example, spin orbit interaction can also bring in ferroelectricity or break inversion symmetry. How? As I told you, this is what is known as inverse of DM effect. So if you have a non-collinear arrangement of spin, which implies that there is a spin orbit coupling, and since you have a non-collinear effect derived by spin orbit coupling, so the local inversion symmetry has to break, which brings in polarization. Well, so improper ferroelectricity has been described, and if you can see that the polarization in these materials is abysmally small, right? So this is what the thing is, and one of the research direction has been that can we have a material, and of course you can see that first magnetism sets in at 41 Kelvin followed by ferroelectric transition, right? So you can see this guy, magnetism sets in first followed by a ferroelectric transition, but ferroelectric polarization turns out to be extremely small. So here displays strong magneto-electric coupling. Of course, there is a strong dependence on electric polarization applied magnetic field or magnetism applied electric field, but magnitude is abysmally small. One of the research thing is, can we have a type 2 multiferroic with a high value of polarization and possibly operating at room temperature? Yes.
So in this case, does it require some critical strength of magnetization before the ferroelectric transition to happen? Is that the reason why the two transitions?
As I told you that to begin with, so above the transition temperature there is no magnetic ordering, right? So you lower the temperature, the magnetic ordering sets in. Once the magnetic ordering sets in, right, it also, so this is what is known as spin phonon coupling, it also starts distorting the lattice. And this distortion essentially breaks, the magnetic structure breaks the inversion symmetry, which brings in polarization. And of course, the strength of the magnetism, so you cannot have it with all magnetic atoms, right? 3D magnetic atoms, which are more localized, they are going to have a better effect. So you can see in most of these cases, right, the manganese atoms are kind of 3D systems. So manganese, vanadium, here is also manganese, and then this is chromium, iron, and copper, right? So 3D systems where the spin or electron correlations are strong enough, right, and that's are useful. Does that answer your question? Okay. Good. So what we did, so we could discover a magnetic multiferroic where the magnitude of polarization was 0.55 microcoulomb per centimeter. Of course, it's much larger, but it's an order of magnitude or 2 orders of magnitude larger than this, right? So I'll briefly tell you that how one can go about doing that. So this is a work which was done by my former graduate student Shayantika, and I think Shayantika is soon going to join IIT Bombay as a faculty. And this work we did maybe 5 or 7 years back. And so this is the crystal structure of this alpha Cu2 V2O7. So you have these zigzag chains, right? One chain running perpendicular to the other, right? So this is what the thing is. Copper is in 2 plus D9 configuration, what we wanted, and vanadium is in D0. And then what you have, copper is in a pyramidal environment, and that helps to have a cooperative giant telemetry. I'll not get into this thing. So effective magnetic moment is something like 1.92, and we have an antiferromagnetism with canting. So this is what it is. But the crucial thing is that we have a ferroelectric polarization which is 0.5 microcoulomb per centimeter square, which we called a giant ferroelectric polarization. So if you do the non-interacting part of the electronic structure, so you can clearly see here, for example, the local distortion essentially keeps this, lowers this dz square and occupies this, and all dx square minus y square orbitals are occupied. As a consequence, this is called a ferroorbital ordering. Well, you can derive the spin model for this system, and the interesting part of this system is the spin model. It's not only a nearest neighbor Heisenberg model, but you have a nearest neighbor second, third, and fourth, and our calculation shows that the third nearest neighbor exchange interaction dominates the nearest neighbor and the next nearest neighbor. So, and you can see the third nearest neighbor, the first nearest neighbor, third nearest neighbor exchange interaction happens to be antiferromagnetic also. Well, so this is of course a calculation, and the calculations can be checked by inelastic neutron scattering data. So this is, so once you have the Heisenberg model, go ahead and define a spin Hamiltonian, do a spin wave calculation and compare with, and we can see that model 1, which was proposed by us, right, agrees well with the experimental data compared to the other models which are supported in the literature, which tells that the model that we have derived is a reliable model, right? So this is what the important thing is. Well, so you can calculate polarization. I'll not get into it. So we again calculate polarization using density functional theory, but here this non-trivial effect of Bailey phase comes in, right? You have to go ahead and calculate that. And if you calculate this polarization, of course we calculate a polarization which was an order of magnitude higher, right? But we could get a polarization for an antiferromagnetic structure which is lower in energy, and the polarization instead of becoming 0.5, it becomes 10 times higher. We compute it to be 4 microcoulomb per centimeter square, right? So it shows.
Is there a way to understand why the coupling is stronger here as compared to the, it's clear that this coupling there is weak. I mean,
Yes, so I'll just tell you, right?
Okay.
Yeah, so I'll try to see, yeah. So now what is important thing, what is happening is that, so we have this magnetic structure, and then we allow for relaxation, right? This is what the magnetic order sets in. Does it have any impact on the lattice, right? So what we see that the nearest neighbor distance, right, in the spin models, the nearest neighbor distance that essentially reduces by 7% in our calculation, and of course that has to be taken with a pinch of salt because, right? And the next nearest, once these spins come closer, the others of copper has to go farther away, and that essentially changes by a lot amount, right? And other distances doesn't change. So which essentially tells that the magnetism brings about this distortion. So this is one of the key things which was not happening with the manganese. That distortion was, so here the distortion for it, and this is happening because copper has this orbital degrees of freedom, and this orbital degrees of freedom means 3 electrons, 2 orbitals, so they will allow for this distortion, and this pyramidal environment which the copper had makes this distortion even more stronger. So this is what our understanding is, and this is roughly appears in our calculation. Well, so this is what, so we have ferroorbital ordering, that means copper dx square minus y square orbitals are only occupied, right? And once you have ferroorbital ordering, then you prefer to an antiferromagnetic exchange interaction up down spin, so the spins can hop around, right? And if you can then hop around, they can essentially take advantage of a larger exchange interaction. Well, so this is what is happening. So one can check this by doing a temperature dependent XRD, and that's what my colleague Subham Majumdar did. And what you clearly finds out, so you can see that this D2, right, this second nearest neighbor interaction below the transition temperature increases, and the next nearest neighbor the first nearest neighbor distance decreases, right? Of course, this increase and decrease is much smaller compared to a theoretical estimate, but these do happen, right?
So is there any exact measurements exist so that it can directly tell you?
XAPS measurement doesn't exist, right? I mean, I don't know why they have not done, which will tell you the local environment, absolutely.
It will match.
Right. So this is where the thing stands, right? So this is what, so this is my final slide, which tells, or with this I'll wind up. So orbital degrees of freedom, and that's the most important thing which the manganese did not have, leads to a polar distortion and a ferroorbital ordering, and spin orbit coupling, albeit small, enhances this orbital ordering, that a particular orbital wants to get occupied, right? And this is what is known as ferroorbital ordering. And once you have ferroorbital ordering, there are tons of literature, the guy has to be an antiferromagnet, right? So as a consequence, there is a strong antiferromagnetic interaction. And how will you increase this antiferromagnetic interaction? Bring the spins closer to each other. Then the hopping increases, because antiferromagnetic interaction roughly goes as 4t square by u. The t, to increase the t, the distance has to be lowered, right? And that is happening, that causes helping the distortion, and that gives rise to stability, and this such an exchange friction leads to large polarization. Well, so with this, I think I could share some of the excitement of quantum materials, and thank you for your attention.
There are questions?
Yeah.
This mechanism can occur in metals like such as VSA2 if magnetism occur.
See, metals, you can never have polarization. So to have polarization, it has to be. So people are these days talking about metallic metals showing ferroelectric polarizations or electric polarization, but traditionally ferroelectrics have to be an insulator. The reason is very simple. Otherwise, if it is a metal, the conduction charges will screen out everything, right? So you will not have any dipoles. So first it has to be an insulator, and if that insulator happens to be a magnetic, then you can expect for a coupling between the two, and there can be an independent coupling which happens, for example, in bismuth iron oxide. But if you can have a system where magnetic order promotes the breaking of the inversion symmetry, that will be even better, even great, right? So that's what I showed you in one of this. So metals will not really play a good role.
So is this transition simultaneous or is it like two different temperatures?
So it's not simultaneous. I showed you this table, or maybe I don't know the time, because I think I have eaten my time. So you can see it's not simultaneous. So here for this TBMNO3, magnetic transition takes place as 41, followed by a ferroelectric transition temperature. Right? In some cases, both can be simultaneous, but the magnetic transition is a primary order parameter. Then the ferroelectric transition, so these are secondary order parameters. So if you want to do a Landau-Ginzburg kind of stuff, right? So you have to have these two order parameters, right? One primary, one secondary, and then bring in a coupling between the two and see what happens.
Sir, in copper-based oxides, like so you mentioned spin gaps.
Yes, so for example, if you have a uniform Heisenberg chain, right? So you know that the spectrum of this, so the ground state is separate from the ground state and excited state doesn't have a gap between them, right? But for example, if you bring in a frustration, or I did not talk about it, or if you have a dimer, right? If you have a chain where two spins are interacting, but not the others one, that interaction is weaker, right? So then you have this, if you look at the spin wave spectra, then the ground state will be separated from the excited state by a gap, right? And this is what is known as the singlet triplet gap, and this is what is known as spin gap. So one of the important why people care about it. People care about it is that you have a spin gap, since the ground state is of course a spin singlet, but if the gap is small, then you can excite it a triplet thing, and then if you lower the temperature, then there can be a Bose-Einstein and condensation of these guys, right? And which can have very important properties, right? Higgs oscillations and so on and so forth. So that's an important thing which people talk about.
So what is the reason why quantum effects dominate in the 2 dimensions and 1 dimension over 3 dimensions?
Yes, because of the fluctuations, right? So fluctuations are, so if you see, you know, right? I mean, we know from our study in magnetism, right? If I want to use a mean field theory, higher the dimension, better the mean field theory is, right? So lower dimension, the fluctuations are much more compared to 3 dimensions. 3 dimensions, of course, fluctuations are there. If you can go to infinite dimension, there is no fluctuation at all. So this is what, so fluctuations are more in 1D, 2D followed by 3D, and that's the reason you have this Marmin-Wagner theorem, right? Which tells you that you can never have a long-range order, right? For a isotropic Heisenberg model in 2 dimensions, right? But still you see 2-dimensional ferromagnets. Why that is the case will be a story that I'll going to share with you tomorrow.
So in most of the systems that you showed, there was like specifically the copper systems, the orbitals had like definite atomic order, so to say, like it was separated copper D and then we have strontium S and P. But what if these states are not effectively atom-like, but like they hybridize strongly? So then how would you sort of extract?
Yes, so for example, this hybridization is much more pronounced. For example, for the d electrons or d states are anyway much more localized, right? So as a consequence, these effects are, so for example, copper will definitely hybridize with the oxygens, and that it does in the case of high temperature cuprates, and there you don't have a Mott insulator, but you have what is known as a charge transfer insulator. That happens, right? So you have the oxygens p states between 2 copper d states in the insulating state. That's the reason they are called charge transfer insulator. So that can always happen. But the thing is that, for example, in true Mott insulators, they are really localized, so like strontium vanadium oxide is a Mott insulator, where I can extract these things out. When I talked about high TC cuprates, right, I told you that the hopping is not confined to nearest neighbor, right? For the mercury oxide, the hopping was much more long range compared to lanthanum cuprate oxide. So this is the effect of the oxygens, right, which was essentially captured in an effective model comprising only of copper dx square minus y square. So these hopping by the through the ligands or other atoms are important, should be taken into account, and that gives important changes, which is also reflected in the experiments, is something I think some of us pointed a long time back.
Can I ask one question?
Please.
Yeah.
Yeah, so in your model for the high TCs, when you said about the hopping and so on, do you have a control what happens to this hopping when you go from an underdope to an overdope to an optimal dope system in high TC?
Well, so our thing is only for optimally doped high TC cuprates, right? Underdoped and overdoped is, I think, is a Fermi liquid thing, so it should work out. But underdoped people have done. So underdoped, of course, is a very tricky situation where, so underdoped is essentially a correlated metal, right? So in a correlated metal, so its screening is incomplete, right? So there is some screening, there is not no screening. So there the hopping gets modified. We have not done that. But for example, a DMFT calculation exists from the Rutgers group, where they show that this hopping gets renormalized, but the trend is follows. The values changes, but the trend follows. Right, yeah.